Hi, Tim.
Hey, Bob.
How you doing?
Good. How are you?
Can't complain. Let me introduce us. I'm Robert Wright, publisher of the Nonzero newsletter. This is a Nonzero podcast. And you are Tim Nguyen, kind of. I didn't get that quite right? Say your last
Good
name.
enough. It's Nguyen.
Yeah, that was better. Even I know that was better. So you are a machine learning researcher at DeepMind, which is basically Google's AI division now, right? And you're host of the Cartesian Cafe podcast. People may remember you from being on my podcast in your role as someone who's doing their best to debunk Eric Weinstein's theory of geometric unity. That podcast got a lot of attention. If people want to look for it, it's provocatively titled "Is Eric Weinstein a Crackpot?" I believe, something like that.
You chose that title.
Well, actually, you used the word crackpot in the podcast. I'm not going to take sole responsibility for that little bit of tabloid journalism, although I am proud of it. So if people wonder, why would a machine learning researcher be even thinking about Eric Weinstein's grand theory of physics? You are actually a mathematical physicist, right? You have a PhD in that?
That's right.
And that's the answer. And people who don't know a lot about AI may wonder what a mathematical physicist is doing, working on, the kind of AI that gives us large language models and so on. We'll get into that. Let me say first, our mission today is to try to improve my understanding, at least, of how these generative AI things work. By that, we mean, the ones that generate images and generate language and so on. Those all involve, I think, machine learning, and more specifically, I guess, deep learning. That's right? Deep learning being a subset of machine learning, and then a large language model being a subset of deep learning, kind of, right? It's one particular kind. And then the image generation stuff is another particular kind. So, this is going to be a challenging conversation. You are not someone who comes at this from a cognitive psychology background. So it's not like you're accustomed to, in the first instance, thinking of these things in terms of their relationship to our models of how the mind works. You come at this kind of from the other end almost, from math, from really, in a sense, the ground level. But that's why I wanted to talk to you, because you understand, in some sense, what's going on at the ground level, and I sure don't. And maybe in the course of this interrogation, people will get a clearer understanding of what's going on. Now, before I start the interrogation, is there anything you want to say about this?
Not particularly. I mean, I guess this will be. I agree. This will be an interesting conversation because I'm not used to talking about these kinds of topics, say in comparison to math and physics, which I've done much of my career and currently on my podcast. But I think it's good because now I'll get this opportunity to explain in basic common language what these models are doing, and of course. Correct me if I get too off the rails in terms of the technical details.
Now, I will jump in every time I don't understand something, which may lead to a lot of jumping in. I'm not well versed in this stuff. Now, I should say at the outset that this started with an email correspondence where I was trying to get clear on some things, and I think one thing that I believe, based on my limited understanding of this, and that you seem to believe, is that it's just too simple to say that this stuff is the language models are just doing fancy autocomplete and kind of nothing more. So it's not any kind of advanced cognition. I mean, one question I ask you is there within these models a configuration of information that can be seen as in some sense a representation of a concept or the meaning of a word or something? And And you said yes. You think there can be. We did get into a little discussion of whether you took issue with my using a term reverse engineering, where you would use emergence, the emergence of certain kind of seeming cognitive properties. I was saying it was almost as if the AI was reverse engineering the mind from the linguistic output. But we'll get into all that. I mean, the main thing is, I think, for starters, you believe this is more than fancy autocomplete. There's something interesting going on inside these things, even if it's not always clear what is, right?
Yeah, I mean, let's unpack that a little bit. I think one of the things that I was trying to express in our exchange was that this phrase stochastic parrot can be used in a very dismissive way that I think it can be kind of unfair. And the analogy I was using is that you can analogize that to this ultra reductionist statement that something's just a collection of atoms. Say, I mean, ultimately everything is just a collection of atoms. But if you're just going to say that and full stop, I think that doesn't give enough credit or enough observation to the fact that atoms can form higher level structures, and therefore there are there's much more content to that than just merely the fact that they are atoms. And likewise, our mind is doing something remarkable when it's able to produce language and all the other mysterious things that come out of our human nature. It ultimately is a computation coming from our brain. Now, of course, there are many divergent views about consciousness and all that. I don't think we need to get there. I think the point is that if you believe that the mind is a computation and computation is based on physics, then I don't think it's fair to say language models are somehow to be dismissed, because they are also a kind of computation. And I just wanted to clarify that merely because they're doing computation doesn't mean they're merely stochastic parrots. They can be doing very high levels of computation that are sort of reminiscent, if not an exact replica of the kinds of computations we're doing. So I think it was mainly, I was cautioning this sort of ultra reductionist dismissive viewpoint that large language models are mere stochastic parrots. They have enough computational power to do very extraordinary levels of hierarchical processing, and that's what gives them this extraordinary ability to model language. I don't know if I partially addressed some of those concerns, but that's sort of what's going on.
Yeah, the term stochastic parrot was actually kind of made famous, I think, for appearing in a paper that was done by, I guess, a former Google employee or two. It was a multi-authored paper. And of course, it refers, I mean, we know what a parrot is, and most people probably know stochastic refers to kind of statistics in some sense. And, you know, I guess you're saying it's true that in some sense what these models do is just kind of predict what the likeliest next word is to be in a certain kind of context, and that wouldn't seem to imply any understanding of meaning. On the other hand, it's clear that they're doing more than parrots can do. You know, parrots just repeat what we say, and in no sense process the meaning. And these machines act as if they understand the meaning of questions and even answers. And I guess, you know, and let me just say what I mean when I loosely refer to these things as understanding or having a conception of meaning or something. I don't mean they have the feeling we have when we understand something. I don't know if they're sentient, if they have subjective experience. I'm agnostic on that. My point is that when we have the feeling of understanding the meaning of a word, there's something going on in our brain, and when we, you know, when we think generally, there are things going on in our brain, and it seems to me there's evidence that what's going on inside these machines has at least something in common with what's going on inside our brains. It's certainly nothing like an exact replica of the structure and functioning of our brain, but I can elaborate on what I mean by that, and maybe it would be a good idea to ask you if you agree. But first of all, does that make sense as a way to think about this?
Yeah, and I think it would maybe be helpful to clarify what we mean by understand, because that's such a vague word. It's not even clear to what extent that's a scientific word, in the sense that can you perform an experiment which would confirm or disconfirm whether a language model understands something. I think ultimately at a higher level, with the word understand and many other words, we're just not used to understanding advanced forms of intelligences other than ourselves. And we're in this sort of phase where things are very, how do I say, there are bits and pieces of it, and there are many gradations of it. And in some ways, these models mimic us. In some ways, they make very dumb mistakes that no human would make. And so I think we have to get used to the fact that there's a spectrum of things, and we're sort of used to using things in a much more binary way. Like, we understand things, but other kinds of, I don't know, animals, species, intelligence, whatever, don't, right? So I think we have to stop being so kind of binary, or maybe anthropocentric in some of our terminology.
Mm-hmm. At the same time, we do make mistakes, and we confidently make assertions that are not true. We're designed to do that, I honestly think. And so I wouldn't, I wish people wouldn't get too condescending toward these machines, especially since they seem to improve with every generation. And their error rate may, before long, be well below ours. But
Sure.
Go ahead.
Yeah, and a thought occurred to me. I mean, in some sense, from a purely instrumentalist perspective, these models do show a great degree of understanding. I mean, you can ask the question, like, does AlphaGo understand Go? I mean, it doesn't have a mind like a human. It's very narrow. It just plays the game of Go, but it does understand it to the extent that it's superhuman and can process many moves and play the game at a higher level than any human, right? Mm-hmm. So I don't think understanding is necessarily, it has some eureka moment in its mind, or it has emotions while it's playing the game. From an instrumental perspective, it understands the game of Go, at least in one sense of understanding,
right?
A valid sense of understanding.
Or to take a more elementary example of understanding something, I understand that both a basketball shoe and a hiking boot are kind of members of the same category. And I would guess that when I think of a basketball shoe, there's a set of neuronal firings or some kind of pattern of physical information in my brain. And then when I think of a hiking boot, there's another pattern. And I would guess that there's actually some overlap in those two patterns. And there's more overlap between those two than there is between either of them and the pattern that's triggered when I hear the word avalanche or something, right? I mean, that's a pretty reasonable conjecture. And I think we have reason to believe that is going on inside these machines in some sense. It's not the same kind of pattern. It's not literally neuronal firings. But I know I heard Jeffrey Hinton, sometimes called the godfather of AI, say something like that. And we have pretty good reason to believe that what I said is true, right?
Yeah, I mean, you can actually confirm this in various ways, and I can go into the weeds in a moment if we need to. But there are all kinds of interpretability methods in terms of probing the neural networks. And indeed, there are representations, as we'll discuss. I think words are assigned vectors in these large language models, and you can look at how close different vectors are to each other. And what you will find are they're semantically related concepts. If you look hard enough, you can find associations, mathematical patterns. And as you say, sort of the notion of nearness, that's a mathematical concept, and you can see that reflected. Now, it's very hard because there are many words. It's a huge computation. It's sort of like as hard as looking inside a computer and saying, where inside the computer's circuitry did it know that to do this computation, or that these two things were similar. But there are sort of toy examples and an increasing level of research that can sort of probe these representations. And so in terms of similarity of concepts, that's actually kind of a low-hanging fruit in terms of if that's the bar for understanding, then certainly these models understand in the sense of forming concepts and being able to do a concept association. That's definitely one of the things that's happening. So you said
nearness. So in other words, basketball shoe would be nearer hiking boot than it is to avalanche.
Yes. Let me just caveat that in that, for example, let me just go slightly into the weeds. Here's a very famous example. There's an algorithm called word2vec, which was developed in 2013. So word to like word, and then the number 2, and then vec is in vector. So it's just a name of an algorithm, word to vec. So basically, you just go through a corpus of text, and for each word you find, you look at its neighboring words, let's say 2 to the left and 2 to the right, and then you encourage the word in the middle. So let's say it was shoe, right? To be, that vector should be near the vectors that are the vectors of the words that are nearby. So let's say it was basketball shoe in this case, right? So I put on the basketball shoe today, right? So then basketball and today were right next to the word shoe. So the vector for shoe would be encouraged to be near the word basketball and today. And the idea is that as you go through large corpuses of text, the word shoe will be more encouraged to be closer to words that are more meaningfully tied to it than words that are not. So
you mean in terms of output, it's being encouraged to output words that these words in a form where they're next to each other or near each other?
So actually, let's back up. So okay, so a vector is.
I mean,
just
what's being encouraged?
Yeah,
is what I mean.
Right. Yeah. So there's a vector is just a list of numbers, right? So let's just say in this case, for simplicity, it's a list of 10 numbers.
Should I not think of a vector as like an arrow on a 3-dimensional graph? That's one way you think of it, right?
That's like the canonical way of visualizing it. Okay. So if you, 3 dimensions is the most number of dimensions that
my brain can handle. Yeah. So let's do that.
Right. Yeah. So just think of this as a 10-dimensional space. It's an arrow now in 10 dimensions. So you have all these arrows for each. So what you do is in all these algorithms, you start with a randomly assigned collection of vectors. So say there's 50,000 words. Each word gets a random vector. And what happens over the course of this algorithm is that vectors start getting pushed towards each other based on which words are near to each other. So imagine this is
during training, during so-called training on texts.
That's right.
Vectors are encouraged to be near vectors they should be near based on frequency in the text.
Yeah. So in this I'm just going to make up this cartoon now. Imagine, there's all this is chaos of 50,000 vectors, and this little goblin is going around and grabbing collections of words that are nearby and sort of pushing them together, right? And it's doing this every time it goes through the corpus. So you have this sliding window that just keeps moving, and that gives you a window of 5 words, and those 5 words just keep getting squished together. And the point is, so in the case of shoe is going to appear more closely to basketball more often than the word today, right? Because today was just incidental. A basketball shoe is an actual thing. So when you have enough text, those statistics will manifest itself in basketball shoe and occurring more often than shoe today, right? And so at the end of training, you now have words where the similarity of the associated vectors capture some kind of semantic meaning. And here's a very famous example. So let's look at this SAT style analogy that king is to queen what man is to woman.
Oh yeah.
Okay. So I think we all understand what that means, right? So king and queen are royal positions. King is the male version of the male monarch, and the queen is the female monarch, right? And so there's king and man, and then so it's king and man, and then queen and woman, and so you can think of this.
We should say to people listening but not watching, you're using are those supposed to be vectors, your finger and thumb?
Let's think of it as vectors, right? Okay. So I'm using my
So king and queen is a finger and thumb on one hand. In other words, one-dimensional kind of vectors in 2 different directions, maybe along 2 different axes, and or something. And then your man-woman hand is the other hand doing the same thing. They're kind of both L-shaped. Okay.
Yeah. So, okay, let's do that. Yeah. Okay. Let's do king and queen on one hand and man and woman on the other. Or actually, I think it might be easier.
Wait,
let's do it the other way. It's going to be easier the other way. Let's do king and man and queen and woman
on the other hand. Okay.
Right. So, what's going to happen is that if you do something like take the vector for king minus man and then add it to queen, you're going to get woman based on this kind of geometry that I just drew here. So if you if you're watching this, right, there's a thing you can add to king to get man, and there's a thing that you can add to queen to get woman, right? And they sort of point in the same direction. It's sort of like the royalty direction conditioned on gender. And so what happens is if you kind of take this difference between king and man and add it to queen, you're going to get woman. And that's exactly what happens. At the end of this algorithm, you have 50,000 vectors, and using the analogies you would get from this SAT style kind of analysis, you can sort of start taking combinations of vectors and get results as you might expect. And that already is sort of like the 2013 way of showing how word associations are captured by these sorts of
statistical
algorithms.
You mean the year 2013?
Yeah, this was developed in 2013.
Okay. Now, I thought I heard a version of that where you do some mathematical operation, you wind up with prince or princess. Is that not right? No.
There's probably a version of that.
Where it gets really... Yeah. Okay. So this is interesting. So now, if we only had 3 dimensions, and these models use a lot more, then we might think that words are being located in a kind of a 3-dimensional semantic map, right? That's not crazy, right? I mean, so your proximity, you could like locate, I don't know, could you locate a word? Words would tend to be closer in this 3-dimensional space to words that have some overlap of meaning than to words that have very little. And possibly overlap in terms of usage or the verbs, who knows? But no, actually, maybe not. Anyway, that would be true if there were only 3 dimensions, but it turns out there's a whole lot of dimensions, so we can't quite conceive of the map, but that's still the basic idea.
Well, so there are several things going on here. First of all, yes, there are more dimensions, and with more dimensions, more parameters, you can model more things, right? You could be more expressive. There's more room to move. Typically, these words live in a 1,000-dimensional space, the order of that. So it's a lot larger. But there's one more significant thing, which will probably take us to the transformer architecture underlying the recent surge in large language model success, which is that you can condition these vectors on the context. So going back to your shoe analogy, well, and basketball. Well, basketball means... Well, it means something, right? It's a basketball. Shoe means something, and basketball shoe means something. Now, if you only have embedding for words, then you can't form compound words. You can't disambiguate words, like the word tie. Do you mean the thing you put on your neck? Do you mean the verb tie? Do you mean like a match is tied, right? So already with the single word case, you have problems of ambiguity. And one of the innovations, or one of the things that are made much more powerful with models like the transformer versus this very, very simple word-to-vec algorithm, is that you're able to take in this sentence, you ask a question, and it's able to understand the words in the context of all the other words in the question. So it's context-dependent embeddings now, and that's a large part of why these models are so powerful.
Okay. And just to be clear, if we imagine this multidimensional space as this kind of semantic map, it isn't that the words close to another word are particularly likely to follow it. It's that they mean similar things, right? So you know what I mean? I mean, that is not a map of likely proximity in a sentence. It's a map of semantic proximity, which is a different thing, right?
I see. Okay. So let's back up. Let me just say something at a high level. The amazing thing about...
I'm worried, but go ahead.
Sure. No, the amazing thing about these algorithms is that they typically are very simple-minded, and yet they work very well. And there are, we can discuss why that's the case, but one reason is that with a large enough data set, which is what happens when you crawl much of the internet, is that the statistics sort of work in your favor. So let's go back to the word-to-vec algorithm. You're right. I was using the proximity in terms of how many words away am I, and if I'm within a certain window, I will do this encouragement procedure. And you're right, that has nothing to do with semantics. That's purely syntax. That's purely just words being close. But the premise is that words which are closer have closer semantic meaning than words which are far apart. And that already buys you a lot of mileage. So that's the fundamental reason why the word-to-vec algorithm works. It's saying I can get some semantic meaning purely from this syntactical game that I'm playing. So that addresses, I think, the first of your statements. And then maybe one comment I want to make is that what's going on inside these large language models is much, much more complicated than the word-to-vec algorithm. The word-to-vec algorithm is just this very simple algorithm that I just described to you that's very easy to interpret. These transformer models are much, much, much more complicated. It's not at all. Okay. It's not as easy to understand what they're doing as what I just said. But by analogy, you can think of what they're doing as some kind of, let's say, glorified word-to-vec.
Okay. That's the thing that happened in 2013, that algorithm?
Yes. And Transformers came out in 2017.
The famous,
field moves very quickly.
Now, Transformers are the famous, I don't want to get into this quite yet, but that's the famous attention is all you need paper.
That's right. Right. And it's the T in GPT.
Right. And that happened to Google, by the way. Go ahead and do a little ad for your company, man. Without your company, there would be no OpenAI as we know it. I'll say it. You don't have to.
Okay, sure.
Let's see. But let's back up and address one thing before we proceed further along the lines of trying to understand all this, which is just, I mean, some people may wonder, like, why are you talking as if we're trying to figure out what's happening within these models? Weren't they designed by somebody? You know, and I think the answer is, you know, what was designed by somebody was more like a process for generating models. And I know in our correspondence you brought up the comparison to evolution. So let me throw out a way of talking about this, and then you tell me whether it's more or less right or you want to correct it. But if you imagine that, like, okay, we build a model of something that could loosely be called, I guess, a neural network or a network of neurons, although I don't know anything about actual neural networks that are actually built by computer scientists. But let's just imagine, you know, like a three-dimensional web. There are nodes, there are interconnections, and so on. And what this thing does is it takes inputs of information and generates output through some algorithm, you know, that translates the input into certain, you know, into certain paths. And let's say that the algorithm is actually represented by the structure of the machine, like what nodes are connected to what. Okay, like what pathways are open and what aren't. I mean, this is a super simple example. Doesn't correspond to anything in the real world, but the point is that the mechanics, the physical structure of this network of nodes that are interconnected is going to determine what outputs come out when you put in an input. And let's say on the input side, there's an optical scanner, and there's three kinds of pictures you're going to show it: squirrels, cats, and dogs. And there's three kinds of outputs: the word squirrel, the word cat, the word dog. And you start out with a machine that's just basically randomly built. So you're just going to get it's not good at all. It's as like, you know, it's like you show it a cat, it has a 1 in 3 chance of saying cat. But then you fiddle with we change one connection and see if the performance gets better or worse. If it gets better, you leave that connection. If it gets worse, you change the connection back to where it was. But in any event, you move on to fiddle with another connection. If it improves the performance, you leave it the way you fiddled with it. If it makes it worse, you blah, blah, blah. You just do that like forever until the machine is getting things almost 100%. It's recognized the cats. Now, you wouldn't know if somebody said, well, how exactly does this thing work? You wouldn't know. I mean, you know, but you just invented the process for making the machine better. Now, there is a rough kind of analogy between that, right, and between what's going on with these models, and that kind of explains why we don't fully understand what's going on.
Yeah, I mean, yeah. So you described essentially what machine learning practitioners would call gradient descent or stochastic gradient descent. So you have this large data set. Your model has a bunch of tunable parameters. Each one is a number, or what they might call a weight. And well, what you do is your data set is so large that you can't just show all the examples to the machine at once. You have to break it up into little batches. That's why they call it stochastic gradient descent, because you're feeding it a stochastic bit of the training data each time. So you grab a random collection of whatever, dog, cat, and squirrel. right? You show it those examples, and then it updates its weights a little bit. And as you pass through the data set, it's going to see more and more, and then it's going to get better and better. And so it's this iterative refinement. It's basically doing a search, right? So you have this huge space of all possible neural networks because each weight can be a number, right? So it's a huge space. And the amazing thing about this stochastic gradient descent algorithm is that it's actually able to find a good solution. So I could say more about that, but I don't know if I was just recapitulating what you just said in terms of maybe how a machine learning person might describe it.
Right. And in fact, image recognition was one of the places where a lot of progress was made, right? I mean, we take it for granted. My dog died not long ago, and I was searching for dog pictures, and we take it for granted that you can type in dog and see a bunch of dog images. 20 years ago, I would have thought that was magic. And that was developed with very much the kind of, at some level, the same technology that is behind large language models. Is that right?
I don't know too much, actually, the details about search, but not, I mean.
No, I don't. Well, yeah. What I mean is the image recognition part of the fact that it knows what a dog looks like is a case of deep learning. Well, is it a case? It's a case of machine learning. Is it a case of deep learning?
No. Well, I mean, Google search was built before the deep learning revolution.
No, I'm talking about searching my own archives of photos for dog and getting pictures of dogs. It would have been considered magic 20 years ago that a computer could separate pictures of dogs from cats.
Yeah, so that's definitely deep learning. I thought you just meant like Google image search in terms of putting in dog and getting.
Yeah.
Okay. Yeah. So the former, the separating dog from cat, that's a deep learning revolution. Yeah.
Okay. And so that was part of the, and in fact, I think the aforementioned Jeffrey Hinton worked on that stuff. Is that right?
Yeah. I mean, I guess if we really want to go, I think the first major breakthrough in sort of image classification, I'm not a historian, by the way, so I take everything with what I say with a grain of salt, but one of the major breakthroughs was by a man by the name of Yann LeCun. He was one of the Turing winners along with Jeffrey Hinton and Yoshua Bengio. He developed what are called convolutional neural networks back in '89, I believe, when he was at Bell Labs. So that was a new architecture at the time, which was also inspired by our own visual systems. But anyways, it made a lot of progress on what's called the MNIST dataset, which is the standard toy dataset that everyone learns and uses when they first start out. It's just classifying digits from 0 through 9. So it's a very simple data set, but it's a good way to kind of get your feet wet in the subject. And then from there, I guess the really big revolution was in 2012, this so-called AlexNet moment, when Jeff Hinton and his students, Ilya Sutskever, who's now chief scientist at OpenAI, and Alex Krizhevsky, they did much better on the ImageNet image classification dataset, which is this large benchmark for classifying all kinds of images. There's like 1,000 categories, and the images are quite complicated. So they got a huge boost and improvement by using these large neural networks. Also these it's also a convolutional neural networks, a much more advanced version than the one that Yann LeCun developed decades earlier. Anyway, so those are sort of like two, I guess, milestones in the image recognition field.
Okay. And the way the machine learns, I mean, once you've got the machine learning set up, is kind of the way I described it. You show it a bunch of images, you know what the correct answer is, and the more it gets the correct, you want to reduce the error rate. You want to fine tune the machine to reduce the error rate. And when you're done and the error rate is minimal, you've got a good image recognition thing. Same with language translation, which seems pretty straightforward. You got texts that have been translated into French, so you kind of know, and maybe multiple translations. So you have several acceptable answers. You can do that. And then with the large language models, I gather the way they're trained, that it's a little less obvious, but I gather the way they're trained is they show them text and they like black out a word. Like they take text from the internet or something, like a couple of sentences, and they black out a word or black out a phrase, and they have the machine guess what's in there, and they want to reduce the error rate there, right? Is that roughly right?
Yeah, let me say there's several different ways to train these transformer models. So the transformer has basically two flavors. There's let's say the encoder flavor and the decoder flavor, and you can combine the two. The famous ones involving ChatGPT, the ones that can chat with you, they're what's called decoder only. They're trained to predict the next word. What you just described in terms of blacking out, that was another Google invention. It goes by the name of BERT. There's like these funny Sesame character acronyms. Machine learning people love to use funky acronyms. So first there was Elmo, then there was BERT, both Sesame Street characters. So BERT is this sort of, it's this encoder style transformer that learns how to predict the words that you masked out or blacked out, as you said. So there's many ways you could train these models. I don't know if you want to go down that rabbit hole, but that was just one of the ways. It's not the way that ChatGPT was trained. That's kind of a technical issue, but yeah, there are sort of different kinds of objectives you can use. I mean, in fact, a large portion of machine learning is the discovery of what are the right objectives to optimize for, right? So machine learning is ultimately about training is about optimization. One way to phrase it is that there is something you're trying to either maximize or minimize. Typically, people talk about minimizing something. So instead of, say, maximizing accuracy, you're minimizing error rate. And the terminology is you're trying to minimize this so-called loss function. So there's something that's like the error rate that you're trying to minimize. We can get into that, but you're trying to minimize something, and minimizing that will track performance gains over the course of training.
Two quick and related questions. Is it easy to say in English, more or less, how ChatGPT was trained? And is that the same way that Bard was trained, kind of the Google equivalent? I mean, are they just in a category of models that use a method of training that's different from the black out the word training?
I mean, they're both similar in the sense that the models which involve generating text. Actually, the distinction is basically: are you generating text or are you not? The models which generate text have to predict the next word, and so they're trained like that. That's what ChatGPT and Bard are doing. This thing called BERT that I told you, there the use case would be something like what's called natural language understanding. So there it would be something like, my task is only to understand whether this review has a positive sentiment or a negative sentiment, or to do some kind of co-reference resolution. These sorts of like language related tasks, like does this pronoun refer to Bob or Tim, depending on how it's used in the sentence, things like that. So for kind of like multiple choice questions like things where it's not just free form response, then this blackout style things is a good enough way to learn the properties of language. But if you want to generate words, if it's just generate rather than classification, then you do this sort of ChatGPT style training. So that's the short answer.
Okay. And there's a question. Well, maybe I'll say. Let me throw it out there.
Actually, can I say one thing? Because I think this is an important piece of information. What's a little misleading about what we just talked about is so we talked about stochastic gradient descent in terms of tuning the knobs until you learn the training data. Mm-hmm. In some sense, that's not the real mystery of deep learning. The real mystery is that it generalizes to unseen examples. Okay, so if you have a big enough machine and enough parameters, which these models do have, it's not surprising it can learn the training data. It can just memorize. I show you a million dogs and cats. Now, it's not surprising that with a large enough system, I can tell you what a dog and a cat is if I've already seen it. What's surprising is if you show me a dog or a cat that I have not seen, and I can recognize whether it's a dog or a cat. That's the surprising thing. So, and in the case of ChatGPT, what this is saying is that, okay, fine, I can complete sentences if I've seen the prefix before. If you give me a question that I've been trained on in Wikipedia and I can answer it with the Wikipedia answer, that's not surprising. I can do a Google search to answer that, or I can memorize it too. What's surprising is that given all these examples, you actually can start answering questions in novel situations. And that is arguably a sign of understanding, that it generalizes. Okay? So to summarize, it's not surprising that you can get zero error rate on the trained data set. That's just mere memorization. The thing that's surprising, the magic behind deep learning, is that it generalizes. And let me say one thing further, which is that this was very surprising also from a theoretical standpoint, because you have many theoretical results developed I don't know, maybe in the 90s or something, that suggested that this kind of result was impossible. If you were a theorist in the 90s and didn't see what was going on, didn't have the foresight, then you would have thought, oh, this is crazy, because if you have such a large neural network, it should just overfit. We could talk about that in a second. But theory would have told you that this should not be possible. And sort of the empirical work sort of disbanded all those wrong beliefs.
Well, in a certain sense, it's generalizing, even if it does something as trivial as recognize a picture of a dog that it's already seen, but a picture taken from a different angle. I mean, that's a form of generalization.
Yes.
But I gather it could also generalize to whole like breeds of dogs it hasn't seen. Like if it hasn't seen any terriers, it could still handle a terrier, or at least distinguish them from other mammals or something.
Well, this is an active area of research because machine learning systems are brittle. So you can run into unfortunate situations like the following. Like you can have let's say you have a classifier distinguishing camel and horse, right? The problem there is that horses tend to be on greener backgrounds because they're around grass, and camels tend to be around more yellow backgrounds because they're around sand. And then what happens when you have a cat in the desert? Then it's going to think it's a camel because of these spurious correlations. So this is a well-known failure mode of these neural networks. They can just be detecting spurious correlations.
Okay.
I guess in that example, I should have put a horse in the desert. Okay, so then they would misclassify it as a camel. But you get the point. So
right.
So there are these kinds of common failure modes. The nice thing about language is that unlike images are much more noisy. There's like an infinite amount of irrelevant variation, right? The background, things like that, the lighting. Text is much more it's discrete, right? It's just units of words or characters, and it's more constrained in that regard. There's more structure to language than there is in images, and so I mean, of course, languages still have problems with generalization. Sometimes you'll type something into ChatGPT and maybe the output isn't quite what you expect it to be, but somehow it's I think the more catastrophic failure modes of generalization you'll find more often with images.
Yeah. Now, maybe we should talk a little about the famous "attention is all you need" paper and try to get a sense for what a transformer is, which I don't. I think I understand. I mean, I gather, does attention refer to kind of attention to context, to
That's exactly right.
surrounding words?
Yeah.
Kind of.
Yeah.
But didn't they know that before 2018 or not? Didn't they, in some sense, appreciate the importance of context or not?
Sure. Yeah. So like I'm not, I'm very much, actually, it's funny because in the field of machine learning, at least in the industrial setting I'm in, sort of things have become much more of a software engineering culture because engineering has gotten so many gains. In other words, there's been a lot of work in academia trying to do computational linguistics, dating all the way back to Chomsky, who's famously very dismissive of large language models. But anyways, right, there's this huge field of computational linguistics where you understand parse trees and things like that. That goes all out the window with these transformer models because basically you build a large enough box of parameters and the parameters sort of learn how to do all that parsing behind the scenes without any need for me doing the coding or training the models. I don't need to understand any of that. The transformer is doing it all the heavy lifting, right? So the engineering has supplanted sort of domain knowledge. So in that sense, okay. So to answer your question, people pre-deep learning, pre-machine learning, were trying to understand things by hand and do algorithms that were handcrafted, right? Where there's interpretability because you're putting in by hand every little rule or whatnot,
right?
And then deep learning comes in and sort of destroys all that by saying, you know what? I'm just going to let compute and data do all the heavy lifting for me. I just need to get good enough data, create a good enough wiring of all the neurons, which is what this transformer is doing, and then the algorithm will just learn all the rules for me behind the scenes. And now the trade-off is that even though it's doing a great job, because these weights are just this big list of numbers, and which I have a hard time understanding as a limited human being, I now have this very complicated algorithm that I don't know how to explain. So there's sort of this performance and interpretability trade-off.
And is it possible to say what weights means conceptually? You hear this term, how things are weighted, or what, is that the kind of the strength of a connection between two words, or what is that?
Yeah. let's go back. Basically, these neural networks are large linear algebra machines. Okay, so there's all these matrices going on.
Linear algebra being the high school, like a plus b square equals whatever. That's linear algebra, right?
In some sense. Do you know what a matrix is?
Vaguely. I mean, it's got columns and rows.
Exactly. Yeah. So you could basically linear algebra is adding and multiplying numbers in these large, let's say, boxes. These large, like you said, rows and columns. Maybe just a simple example, just so that we have something concrete. Actually, let's back up. Before you can understand these complicated models, the building blocks of these large models is linear algebra. And the way linear algebra comes up is you want to have matrices multiplying vectors. Why do you want to do that? Let's just look at, say, a simple example of, say you want to predict the price of a home in terms of various properties. Okay, so how would you do that? You would try to come up with a model that's produces the value of, say, the home in terms of some of its features. Let's say the size in terms of square feet, and say the location, right? Mm-hmm. And what you would do would be to say, I'm going to assign a weight to each of those numbers. So maybe per square feet, maybe it's like, let's say, I'm just picking up a number, $10 per square feet, $100 per square feet. Mm-hmm. Then you'd have like 10 or 100 times that number. And then you'd add in these other features that you would weight. So the weight tells you how important each of those features are. Mm-hmm. You add them all up, and then you get the price of the home, right? So that is an example where a matrix multiplication takes in the input features, which are whatever, the square feet, location, which you could think of as a vector where there's a 1 in a position, depending on where it's located. So maybe in three-dimensional space, there's a 1 if it's in the US, a 1 if it's in the UK, and a 1 if it's, I don't know, in South America, right? And there could be more entries if there's more locations, but basically the position of where the 1 is will tell you. I'm just trying to come up with a vector for.
Right. So in that case, variables like square footage are being assigned weights that reflect their importance in determining the value of a house.
Exactly.
And in the language model, what is being assigned weights?
Yeah,
reflecting their relative what?
Yeah. So let's back up for a second. So in this case, if you wanted to actually fit this model to get a good model, what you would do is you'd scrape a lot of data about houses and their properties, their prices and whatnot, and you'd learn the weights such that the error is minimized, right? Mm-hmm. And so you have a handful of these weights. You see them; they're in front of these features, these properties, and you just learn them. A similar thing is happening in these transform models, or all these models. In fact, you have a bunch of these weights which multiply the inputs. And what happens is you iterate. So you have layers. You have layers you can think of as parts of a sequential computation. So you have the input layer, your image, your piece of text. Mm-hmm. Then you have a module that has all these weights and does all this fancy multiplication and whatnot. And then it hands it to the next layer. And what's key is that you have to have some what are called nonlinearities so that you get more complicated functions. Because as I can explain, if you keep composing matrix multiplications, you just keep getting a linear function, and not all things in life are linear. If you look at the price of a stock market, it's not linear, right? There are ups and downs. It's very jaggedy. So if you want to model jaggedy things, which is what is the real world is jaggedy, then you have to start introducing what are called nonlinearities. And so the amazing thing is you just keep composing all these multiplications, all these nonlinearities, and eventually you get a complicated enough transformation that you can actually model real world phenomenon.
Mm-hmm. And we should say that at the very beginning of the process, the text is converted into mathematical form, right? Mm-hmm. I mean, first it's broken down into tokens, which are not exactly the same as words. I mean, some tokens are words, but some tokens, and I don't really totally get why this is, are just sequences of letters, or maybe they're phrases. I don't know. But what is the deal with these different forms that tokens can take before the tokens are converted into numbers and then subjected to all this math?
Yeah. So let me say, yeah, I've been speaking at the level of words because it's just conceptually simpler, and that's sort of an orthogonal difficulty to go into subwords and things like that. But yeah, it's true that actually you do break up words into characters or pairs of characters or things like that, and you assign vectors to those. I think that's a less interesting detail. We could just pretend things are words just to be simple, because that's just an added difficulty that doesn't add much insight.
But I guess it is a little puzzling to me why, like, just 2 consecutive letters in a word turns out to be meaningful from the point of view of the model, right? I have a conjecture, but it's not intuitively obvious why anything other than words and phrases would be worth encoding.
I see what you're saying. Yeah, like it seems naively like, okay, like if I encode characters A through Z and then pairs like A, B, A, C, why should that have any semantic meaning? And this is precisely where you need to start group when you have to start getting representations that take into account the context and the groupings of them, right? So you do have to understand that CAT, cat, means something more than just the individual C and the A and the T, right? And actually, maybe just going back to this thing about weights, what we just talked about, like, for example, like if you want to know the difference between a cat and a dog, one thing would be, okay, a cat has whiskers, a dog doesn't have whiskers, right? So if you could find a way to say, oh, in my vector, there's a coordinate that measures the whiskeriness. I can assign a score to whiskeriness. Then a high whiskeriness should correspond to a cat, and a low whiskeriness should correspond to a dog. The problem is, how do you assign a whisker score to a cat or a dog, right? By hand. Like I don't know if a good, like you could say, oh, maybe look at this part of the image. But the problem is that if I just slide the cat over to the right or to the left, that's going to destroy your algorithm for saying, oh, a whisker is somewhere specific to the image. So the magic of deep learning is that it's assigning these vectors. You don't know what those components are, just like in the case of the house, where you say, oh, the first component was the square foot, the second component was whether it was in the US, the third is whether it's in the UK, etc. So the amazing thing of deep learning is that you just sort of initialize things randomly, and it learns how to assign the features and the scores themselves. And that's why it's hard to understand, because you don't know, you didn't bake in by hand, oh, this thing is where it used whisker detection. This thing is where it used square foot. This thing is where it did this and that. No, it's doing that all on its own. You have this big list of numbers, which you can think of as some kind of score, but you don't know what it's the score of. So to start from the beginning, you have words, really just, something more granular, but let's just say words. You have words, they're assigned all these scores in a vector, and you keep processing all these vectors, and those vectors look at other vectors. And at the end of the day, you have some higher level vector, which kind of mixed together all these scores, all these vectors from the other words. And it produces this computation that tells you what the next word is. But nowhere along the line did you say this vector or this score meant something. It's doing that all for you.
So is part of the idea that even if you didn't tell it where a word begins and where a word ends, if you just assigned numbers to every single letter, every 2 consecutive letters, and blah, 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 all the way to 20, and didn't say to it, didn't bother to distinguish words, it would still wind up putting special emphasis on things we call words, right? In its model. Is that one thing that's going on here? I mean, I still don't quite understand why you don't just start out and define a token as a word, but that would happen, right? It would implicitly assign more meaning to words than to many other consecutive strings of letters, if that makes sense.
Let me back up, because I think we might be imputing things to the model which it might not have. But the one of the main reasons let's back up. So you can, there's 2 very initial guesses of what you might try to do. You can assign vectors to words, or you can assign vectors to characters, right? If you assign vectors to words, then you have this big dictionary of every word, and cat gets a vector. If you assign a vector to every character, then cat gets 3 vectors, one for C, one for A, one for T. In practice, what you do is something called byte pair encoding. You don't have to go into the algorithm, but it's doing things at the subword level. It breaks up words into basically pairs or triplets of characters. It depending on, it's sort of adaptive, okay? And The reason you do that is to solve the following problem. Suppose you see a new word that you haven't seen before, right? So, maybe it has maybe the word, maybe Timothy isn't in the training in the data, and at test time it asks a question about Timothy, and now it's screwed because it doesn't know what to assign to Timothy. So what it should do is just break down Timothy to maybe T-I-M-O-T-H. And it's definitely seen T-I, M-O, and T-H in the training data because those are common pairs of letters, right? So in many ways, it's to solve the problem of you can't really have an exhaustive list of all the words, but what you can have an exhaustive list of are all the building blocks. And so that solves that problem. And it is remarkable that even though you're working at this more granular level, it still is nevertheless able to synthesize all of that to get higher level meaning. So actually what ChatGPT is doing when it's chatting with you, it's actually producing these sub-word tokens, and it's predicting those one at a time. The way it's rendered, it looks like it's doing word by word, but it's actually doing it at the sub-word level. So it is able to sort of, in that sense, stitch together these sub-word units into word units. Because when you unroll it, it is producing coherent word after word. So I don't know if that addresses your thing about.
Yeah, it kind of does. I mean, it still seems like a slightly odd way to do it, but it works. And I would guess that one thing that actually the algorithm is picking up on is the fact that within words there are semantically significant, at least at a probabilistic level, sequences of letters, just by virtue of, for example, by virtue of the Latin origins of some language, PAT is often going to refer to something male or, father, blah, 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 and so on. And I suspect it picks up in weird ways on the etymological origins of languages in that sense. But, who knows? Okay, so attention and transformers. So how would you characterize the big finding of that paper? Is it that you want to scan a lot of surrounding tokens in order to, I don't know, you tell me. What is the meaning in layperson's language of the attention is all you need paper?
Sure. Maybe let me just use one analogy because I was trying to think about this for myself and that might help. Like imagine the analogy of playing chess, right? Like in chess, you really only can know one move ahead at a time because you don't know what your opponent's going to do, right?
Right.
Nevertheless, if you give me the entire corpus of chess data, even though I'm sort of optimizing for one move at a time, I still learn the global properties of chess that I'm supposed to checkmate or that certain sequences of moves are orchestrated in a coherent way. Like I'm going to sacrifice now to gain an advantage later, right? And so I think that's a good analogy for what's going on in these language models. That even though they're doing one token at a time, because you've fed them a large amount of text and you've given them the entire context, in other words, they only are responsible for the next token, but you did give them the whole paragraph or the whole book. Likewise, with chess, you are only learning the next move, but it's in the context of the entire game. So you do learn the entire game from these sort of learning the local moves. So if you believe that you can learn chess by doing local moves, then it's likewise you can learn language by doing these sort of next word predictions when you're given the entire context. So I don't know if that's helpful, but I think that's maybe one way to sort of fathom this.
Although we do tend to learn chess by having the rules explained to us, whereas with language, that's not the case. We learn language inductively without and unconsciously, right? By just hearing a bunch of it and having presumably some brain structure built in that helps us make sense of it.
Yeah, well, there's learning the rules of chess and there's playing chess. Of course, I'm about playing chess. Yeah, the rules of chess don't tell you how to play chess well.
Right.
Yeah.
Right.
So,
okay.
Yeah. Anyways, I was just trying to maybe make it more understandable how you can get sort of the large objective of emitting a coherent sentence merely from the objective of predicting the next token. Okay, so I maybe think about chess, and maybe I'll just leave it at that in terms of from local to global. But to get back to your question about attention, so the way let's get, unfurl what attention is, and stop me if this is not making any sense. But the underlying mechanism of attention involves three components or three sets of objects. They're called query, key, and value. Okay, so when you are passing your sentence through the attention module, each word, each token, gets three sets of vectors. There are the query vectors.
Now, is this, by the way, query in the sense that I would query ChatGPT? Like,
it's related. I mean, it's not you doing the querying. It's sort of there's a computational query going on.
Okay.
So you have three sets of vectors, one for each word. You have the query vectors, the key vectors, and the value vectors. So you can think of it as follows. So say I have, let's say I have the sentence, the cat is, right? And maybe you want to complete it to like furry or something like that, right? So let's start with the cat is, three words, right? So you're going to get three query vectors, one for each of those words, three key vectors, and three value vectors. And here's what's going to happen. So you have these, in this visualization, you have these three query vectors and these three key vectors. And the first stage of the algorithm is going to say, how do these queries and keys, how similar are they to each other, right? And so what's going to happen is each word, so let's say cat, is going to look at the key vectors of all the other words. So there's the query vector of the cat. It's going to look at the key vectors of all the other words. And based on how similar they are to those query vectors, it's going to assign a weighted sum of these value vectors. Okay, so let me state that again. Words get queries, keys, and values. The similarity between the queries.
Every word has those three dimensions?
Yep, it has three. It's triple. Yeah, right. And the similarity between the queries and the keys tell you what combinations of the values to get. So like I was trying to think of maybe
query plus key equals value in some sense, or those first two variables can be transformed into value as kind of the answer.
Or the query and the key assign a weight to the value. So like I was trying to think of like a cartoon analogy. So you can think of like a query being like a librarian, a key being a book, and the value being like maybe the information in that book, right? So you have like each word is like a different librarian. Each librarian sort of takes a different mixture of like these books, and therefore it produces a different combination of sort of like the information from each of those books. So basically, without going into all the details, you have these systems of vectors which interact with each other, and they tell you what combinations to sort of take from them. And by iterating this process, what you do is you apply this attention over and over and over. And so what you should be thinking of is that these words start looking at all the other words and start taking combinations of all the other words over and over and over until it builds up a hierarchical understanding. So you have a long sentence, right? There are many different noun phrases, verb phrases, references. And as it keeps attending, it keeps weighting different parts of the sentence and stitching them together in nonlinear ways until finally, at the very end, when it has to predict the next token, it's done so much contextual processing that it actually, quote unquote, understands what's going on in the sentence.
No wonder they consume so much compute, as they say in the business. But is query like each word just has a value that is the query value and the key value and the value? I mean, but how do you assign these? I mean, what do humans assign those, or are they implicit?
Those are part of the.
The machine figures them out in a sense.
Yeah. Those are part of the weights that are learned. So there are these matrices that transform. Actually, what happens is at the very beginning, each word gets assigned an embedding, a vector that's learned, and then that vector keeps getting transformed. So that vector gets transformed by a matrix into a query. It gets transformed by a different matrix into a key, and it gets transformed by yet another matrix to a value. And then you do the attention mechanism. It gives you a new set of vectors, and then you pass that off into the next attention module, and you have another set of weight matrices that again performs this transformation. I'm skipping a few other intermediate modules that aren't relevant for the purpose of this discussion. It's the attention mechanism that's doing kind of the heavy lifting in this sense. So this is the sense in which transformers are doing hierarchical processing. You can like in this cartoon analogy, again, nobody really knows because these numbers are so hard to understand, but you can think of it as like, maybe at the beginning it's understanding individual tokens and then pairs of tokens and then triplets of tokens, and n-grams in the language of linguistics. And at the very end, after all this attention computation, it now sort of has an idea of a sentence because it's contextualized, it's sort of mathematically mixed all these words together with the attention mechanism.
So I would be lying if I said I understand all this, but let me ask you this. If you were to getting back this idea of kind of mapping words in semantic space or something, would all three of these variables be important for that mapping?
Yeah, but how I say, this is where interpretability becomes very hard because unlike word2vec, where each word had a single vector, in this transformer model, there are many vectors corresponding to each word because the computation happens in each stage. Think of it as a conveyor belt. It's like I give you a box of words, a sentence. It goes in one part of the conveyor belt. I get you another box of words, and then it gets processed 100 times. And at the very end, you have something. And now your question to me is like, oh, where is the representation for this word? Well,
it's in several places.
It's the whole conveyor belt that is generating these context-dependent vectors, and so you have now billions of parameters operating on these words, which live in 1,000-dimensional space. It's very mind-boggling to try to understand. It's like asking you, like, when you think of a dog, where in your brain, Bob, is that dog? It's like it's all over the place, right? I can't. There's a computation going on.
Yeah. So is the answer though is that if I could conceive of this like 1,000-dimensional space, a word would be located in a number of different discrete areas. In other words, you could pinpoint the place. It's just not the only place the word would be. It would be in multiple places.
Yeah, and it's no longer pure. It's also a context-dependent embedding of the word because after you embed, okay, so you embed the word. That is one vector associated to the word, but at every future step, that step in the pipeline conditions that vector on all the other vectors in the context. So after the first step, you now have context-dependent word embedding, which is exactly why they're so expressive. Right now, it understands that basketball shoe means more than just basketball and shoe. Because after the first step, when you give a vector for basketball and a vector for shoe, again, I'm simplifying because it's actually at the subword level, but if you just ignore that, at the higher levels, it's combined a basketball and shoe together into some other vector. So basketball will now get a vector that gets combinations from shoe and everything else, and shoe gets a vector from basketball and everything else. Because again, the attention gives you vectors for each of the words, each of the tokens in the sentence, and they all sort of get mixtures from all the others. So at every stage, if like the cat is, you always have the query key set of vectors for each of the words in the sentence, in this case, 3. You just keep it all along for the ride. Yeah.
So the phrase attention is all you need means all you need to do these really sophisticated large language models is to kind of pay sufficiently nuanced attention to enough surrounding words or tokens where the nuance includes understanding that each word has more than just kind of one. Well, it has, for starters, it has this query key value thing. I mean, is that kind of it?
Yeah, let me say a thing that will, I think, answer your question. A predecessor to the transformer architecture are what are called recurrent neural networks. There's a version of this called LSTMs, long short-term memory. We don't have to go into the details. But at a high level, how are they fundamentally different than a transformer? What they do is they unroll word by word. So in other words, what happens is if I want to do the cat is furry and I feed you the cat is and I want to predict furry, what happens is you feed in the word the, and then you feed in the word cat, and then you feed in is. And what happens is it's processing sequentially iteratively, and it's doing a computation each new word you give it. The transformer, on the other hand, you feed it the entire sentence, the cat is, and it does a one-time forward computation. So it's sort of, I have to be, I'm not being exactly precise here, but it's sort of not temporal in that sense. I don't have to go word by word. I just feed you the entire sentence, and then it gives you the output from that entire sentence. And in that sense, it sort of attends to everything in a way that these RNNs that I told you about, you have to kind of go word by word. So the attention is all you need. You can think of that as a counterpoint, if you will, to these, what I called RNNs. It's a fundamentally different computational paradigm.
Okay.
Yeah.
So, listen, we've been talking about actually a little more than an hour. And as I told you, Tim, one thing I've been doing on this podcast is make the first hour a public podcast. As always, that's about how long my podcasts have always been. And then doing kind of an overtime segment that is available to paid subscribers of the Nonzero newsletter. And you can become one by Googling Nonzero and Substack, or just by clicking the link on the show notes in a podcast app. And there's a lot of, you get the overtime segments of the podcast, and you get other stuff like the Friday Parrot Room and all the text in the newsletter that's for members only. So I encourage people to do that. And whether it's because they want to listen to the rest of this or because they want to support what we're doing here. But I also thank the people who aren't going to be with us for the rest of this conversation, just for listening this far. And I want to thank you, Tim, for agreeing to stick around for this. Before we transition to that, is there anything else you want to say? We hope to attain more understanding of all this and what follows in the conversation. But is there anything you fear may have been misunderstood, or you want to clear up, or you just want to say and conclude? Like maybe there's just one clarifying thing you've been waiting to say, and I just haven't asked the right question or something.
Not really. I guess we did go into technical depth. Of course, it's always hard to do verbally without the equations, although maybe, I don't know, maybe you or your listeners might not want to hear the equations anyways. But let's see. Yeah, I don't think I have anything particular. I'll just defer to whatever questions you might have.
All right. Sounds great. Okay. Then thanks again to everybody. And we're going into overtime.